Alright guys, so we're going to start right where we left off. The last thing we were talking about was Alfred Wegener and his hypothesis of continental drift. And we were talking about how his hypothesis was pretty much not accepted because he could not figure out what force was actually moving the plates. Um, and today we know that he was correct. He did have it. He just couldn't explain that piece. Although I don't want you to think he was right about everything. He actually had quite a few things that he was off on. One was he believed the continents were moving about 1 mile a year. Today we know that it's actually maybe about half an inch a year that they're moving. But I want to look at some of the people that really didn't go along with his hypothesis. This guy right here, Charles Hapgood, was someone who was very animate, very much against the Wagner's hypothesis. He demolished this whole idea of continental drift and wrote a book in 1955 where he did so. And the book itself was even had an intro by Albert Einstein that supported his idea that continents do not move. So ultimately these guys were wrong. Einstein was actually wrong. He was on the wrong side of this particular scientific debate, even though he never lived to figure this out, to realize this. He had died before we found the force that actually moves these plates. But during their time, what most geologists believed in was what we call the baked apple hypothesis. That, like an apple, the Earth was at one time very smooth skinned, and over time, from the heat inside the Earth, it did something to the exterior, to the surface of the Earth, similar to what would happen to an apple if you baked it. It made the crust wrinkle, and all those wrinkles were valleys and mountains, and that's how most geologists believed the Earth became such a unique place with all the different features and environments that you see. So you go back to 1950, and most scientists believe this. There's really only about 12 geologists that really truly accepted continental drift. And even into 1980, not that long ago, in the U.S., one out of every 8 American geologists still rejected this idea that continents move. And the reason why, once again, is we didn't know the cause. Uh, Now, fast forward a little bit from Wagner's time, around 1947, we have a group of scientists who begin to map out the Atlantic Ocean floor, primarily for the purpose of submarine travel. All right, basically creating a roadmap for submarines. And they use sonic depth recording, where they just sort of like a bat sent sound waves down, hit the bottom of the ocean, bounce back up, and gave them a reading of what they see. It's also similar to the fish finders you see on boats going up and down Lake Champlain. And as they did this, they found something really unique right in the middle of the Atlantic Ocean, this long 80,000 kilometer scar that we now refer to as the Mid-Atlantic Ridge. And it's a really unique find. We had two scientists who took a closer look at this. Here's kind of a close-up view of that Mid-Atlantic Ridge. And these two scientists were Howard Hess and R. Dietz. And they noted that at the oceanic ridges, they had a couple observations. One, the rocks got older as you moved in either direction away from the ridge. There was a whole bunch of heat coming out of the center of that ridge. And there was a lot of earthquakes happening around the area of that ridge. So with those pieces of evidence, Hess and Dietz were able to pretty conclusively say, hey, you know what? He was right. Wagner was right. These plates are moving. All these earthquakes and all this magma and heat coming up is pushing these plates apart. But still, they weren't able to answer the how. How is it moving? What force is pushing it? And so what Hess and Dietz did is they went back to about 1944 and revisited a scientist who came up with a hypothesis. His name was Arthur Holmes. Here he is. And he wrote a book called The Principles of Physical Geology. Now, Holmes was really known as a geochronologist. Geo meaning Earth, chronology, time. He was able to figure out how old the Earth was. And he actually came up with a really accurate measurement of 4.5 billion years, which we still stick to pretty much today. But aside from that, what he really did for this part of what we're talking about is he came up with the explanation of how these plates are being moved. And what he said was the heat being produced way down in the outer core and the lower mantle from all the radioactivity happening. There's a lot of radioactive elements down there, very heavy elements. And as they're going through radioactive decay, they produced a lot of heat. And that heat creates what we call convection currents in the Earth's mantle. Now, convection current in its simplest form is just when heat rises, cools, and sinks. If we look at this more scientifically, though, and in this example, we're looking at air. As the heat rises from that hot radiator, we know that hot atoms actually are moving really fast, which creates more space between them. And we know if you have something with a lot of space between it, it's not that dense. It's not compacted. And less dense things rise. So the hot air rises up where it gets away from that heater. It cools back down. And as it cools, the atoms slow down. They get compacted back together, making it more dense. And it sinks. And as it flows back over towards that radiator, it heats up again. And you get this cycle, this current. We call it a convection current. Now, what he was saying, what Arthur Holmes was saying, is that this is happening in the mantle too. That as if you look down towards the bottom of the mantle here, towards the core, as that part of the Earth gets hot, it becomes less dense and it rises. When it gets up towards the crust, it cools down, becomes more dense, and sinks. And this creates a really slow motion conveyor belt. And the plates on top of it, which we call the lithospheric plates, the lithosphere, move. So here we have the how these plates are moving. It's from convection currents in the mantle. So really quick, on a side note, I want to tell you more about Arthur Holmes because he had a really interesting life. A lot of it was actually pretty misfortunate. After he graduated from college in 1910, he went over to Mozambique in 1911 and he became a mineral prospector. And while he was there, he unfortunately contracted what's called black water fever and malaria so severely, so bad, that they actually sent a telegraph home announcing his death before he even died. Now, obviously, luckily, he recovered from this, but he suffered the rest of his life from recurring illnesses related to that early exposure. Fast forward a little, in 1920, he joined an oil company in Burma as their chief geologist. And unfortunately, this business went belly up, and he returned to England without any money. But before he returned, really unfortunately, his son had contracted dysentery, which is another little microorganism often found in water, and he died from that, his 3-year-old son. Again, fast forward years later, 1944 is when he published that book we were just talking about. And at this point in his career, he gained a lot of attention, a lot of fame in his field, and actually has several honors named after him today, even a crater on Mars named in his honor. So you work really hard, you get a crater on Mars named after you. So we have the how, we know it's moving. I want to look at a couple of the details here closer because they're very interesting. And I also want to mention that the whole idea of continental drift, that name, is replaced with plate tectonics because we know it's not just the continents moving, that it's actually the whole lithospheric plate, the continents as well as the crust and upper part of the mantle underneath the oceans. So Hess and Dietz uncovered the Holmes convection current idea and put it together with their observations of what was happening at the mid-Atlantic oceanic ridges and came up with this term called seafloor spreading. They said the seafloor at these ridges were actually spreading. And in this image here, you can make out in kind of the tan color all the continents, Africa, South America, and all the really crazy colors there are actually in the oceans. And right in the middle, you can see the Atlantic Ocean, and the red, the dark red, is the mid-Atlantic Ocean ridge. And the colors here represent the age of the rock. And you'll notice that as you go in either direction away from a ridge, you see the age of the rock is the same. You have a red band and a red band. Then it gets a little further out, and it's kind of a brownish band and a brownish band. A little further out, it's yellow and yellow, and then green and green. And you'll notice that these bands are equal distance in either direction from the ridge, and they're of the same age, and they're symmetrical, meaning that those were actually once together at that ridge and have been spread apart, seafloor spreading. Now, the next thing I want to talk about here, along with the Mid-Atlantic Ridge, is what we refer to as paleomagnetism. Paleo means ancient. So we're looking at ancient magnetism on Earth. And we back in the 1950s and 60s, took little boats and we ran right through the Atlantic Ocean, dragging behind it what's called a magnometer, which would read the magnetism of the rock below the ocean. And we noticed that as we moved away from the ridge in either direction, the magnetism, there goes our bell, the magnetism changes. Now, we talked earlier in the year how the magnetism on Earth has not always been the same. You take out a compass now, it points to the North Pole, but there's been times where you take a compass out and it points to the South Pole. We've had reversals in polarity, reversals in our magnetism. And, it's happened several times. It hasn't happened during, human history, but it's happened several times, and we can record that. We can see that because it's been recorded in the rocks. Now, the way that happens is there's iron in rocks, and iron being very magnetic will actually orient itself to whatever polarity the Earth is in, whether it's pointing north or south. And the iron will actually lose its magnetism at a certain temperature called the Curie point, where it gets heated up so hot it actually loses its magnetism. And then as that rock cools down, the magma comes to the surface and cools down, it'll reorient its magnetism to whatever it currently is on Earth. So as we move away from the ridge in either direction, we notice that we have these reversals in the rock, north, south, these bands. You can kind of see it here on this picture, like little candy cane bands of north, south, north, south. And we notice it happens on the other side of the ridge in symmetrical patterns. So we can see that, once again, more proof the seafloor is spreading. Here's a little animation that shows that. You can see the lower right-hand corner, the north-south reversals. And then the colors moving away from that ridge in the middle show the reversals themselves. And the blue are symmetrical on both sides of the ridge, showing that spreading of the seafloor. The kind of a little multiple choice question for you to look at. Seafloor spreading occurs because the answer here is with those convection currents happening in the mantle, it is going to push molten rock up through that ridge, which is going to essentially push those plates apart. So molten material in the mantle rises to the surface. All right, let's go on to something a little bit different here. We know that the plates are moving. We know how they're moving. Now let's look at something else about the plates. So we fast forward during the Cold War with the USSR, with modern day Russia. The US was pretty concerned with Soviet nuclear testing. So we put up seismometers all over the world, and those seismometers were used primarily to see if anybody was testing nuclear bombs. We could actually pick up on that. Now, on a side note, we could use those seismometers also to look at earthquakes. And by the late 1950s, these seismometers were deployed all over the place. They were working 24 hours a day, 365 days a year, and they began to pick up on all these earthquakes, these what we call bands of seismicity happening all around the world. And not by coincidence, as you look at these, they form patterns. They are going around the edges of plates. So as these plates are moving, they're creating earthquakes with the collisions and the breaking apart of rock from the movement itself. And with this, we can now look at where our plates are, the Earth's plates. The Earth has approximately 8 major plates. We're on the North American plate, all of us except for the southern part of California, which is actually in the Pacific plate. And if you look at it closer, you see there's a whole bunch of little plates as well. So there's about 8 or 9 minor plates for a total of around 17 or 18 plates, major and minor plates. Although some resources will tell you anywhere up to 30 to even up in the realm of about 60 plates, but they're really getting nitpicky and looking at a lot of kind of newly forming plates that haven't been well defined yet. And that's going to be the end for this part of our lecture, and I'll see you in class. Bye.